Hi, I'm István Sárándi, and I will present Localizer fields for continuous 3D human pose and shape estimation, or NLF for short. NLF is a state-of-the-art single-image 3D human pose and shape estimation method jointly trained on 50 datasets. One big challenge when bringing together so many datasets is that they use different types of annotations, different body models, or different skeletons. A few recent works have tackled multi-dataset training for this task, but they are formulated as parametric regressors for a specific body model, typically simple X. This means that other annotation types either cannot be used or must be converted, which is prone to errors. Predicting parameters also tends to result in misaligned predictions on the image. In contrast, our goal is to directly train on any type of annotation without error-prone conversions, and to offer any output format at test time. We also aim to improve 2D alignment. Our core idea is to formulate human pose and shape estimation as a continuous point localization task. Here's how that works. You have an RGB image. You then freely pick any set of points in the canonical space. These can be on the surface or inside the body. Then our model returns the estimated 3D location of those points in the camera coordinate system. What do we gain from this formulation? First, we can now directly use any training annotations, since all of them boil down to localizing some key points. The difference only lies in which ones. Second, the model remains flexible at test time as well, so any skeleton or mesh can be predicted with it. No retargeting is needed. Third, estimating individual points yields good image alignment. But how can we build a model for localizing arbitrarily chosen points? We start from the established 3D pose estimation paradigm of building volumetric heat maps and decoding them with soft argmax. In the common case, a 1x1 convolutional output layer will have separate weights for each joint that the network is trained for. If we want more joints, we would have to extend this layer with more parameters and outputs, which is not scalable. Instead, to predict arbitrary points, we introduce what we call a localizer field. To indicate which points we want to predict, we simply select them in the canonical space. The coordinates of each canonical point are then fed to a neural net, the localizer field, which sets the final convolutional prediction layer's weights to make it predict the desired point. This is therefore a simple hypernetwork and is trained end-to-end. The localizer field itself is built analogously to other neural fields defined over 3D space, starting with a positional encoding and continuing as an MLP. Here's how it looks when we densely query points along a path in canonical space. We project the prediction onto the image for visualization, but these are 3D predictions. To train NLF, we sample batches across 50 different datasets with different annotations. We do not have to convert them to a single representation. For each training example, we simply query and supervise the points that have annotations. After it's trained, the model can function as a mesh estimator or as a skeleton estimator in any user-chosen format. So far, this method gives us non-parametric output. However, for the case when parametric representation is desired, in a format such as simple or simple X, we propose a simple post-processing step to fit them. It turns out that this can be done orders of magnitude faster than existing optimizers when the input vertex and joint predictions already have a high quality, as with NLF. See the paper for further details. NLF achieves state-of-the-art results by a large margin on the 3DPW and EMDB standard pose benchmarks, and also outperforms prior works on the SSP 3D body shape estimation dataset. It also performs well in the wild, even for highly complex and unusual poses such as this one. In summary, NLF is designed to localize any freely chosen points of the human body. This way, we can train on many datasets without having to convert annotations. We achieve state-of-the-art results on several benchmarks, and we will release our code and models for research. Thank you.